Thank you, Eric, and thank you to the organizers for inviting me. And thanks to you folks for coming this morning. I had visions of speaking to an empty auditorium after such a good party last night. Wasn't it a good party? Yeah? Yeah, so I would like to tell you a little bit about how nanoscience can help us answer some of the questions that are important for society. Not only now, but in the time of our children's children. Nanoscience has not had a very good name in the past few years because people who don't understand think that all the new products produced by nanotechnology are bad for us, not realizing that we have had nanoparticles around since the beginning of time. And we eat them and we paint them on our skin and so on. But I don't want to talk to you about nanoparticles in the environment, so if you're here for that, then, well, sorry. What I want to do is tell you about how nanotechnology, the machines that have been developed for nanoscience and technology, can be used to get answers to questions that are of importance to us and to our children's grandchildren. So, what do I mean by this? Well, this is home. It's where we live. We breathe and we eat and we drink and we try to stay warm and we like light because darkness bothers us, and it has since the beginning of time. We produce garbage from all these things. We have since the beginning of time. And if we don't deal with that garbage, it can poison us. So now how can we use nanotechniques to tell us about the interface between solids and fluids in a way that can help us understand nature and solve some of these problems? We need to make sure that we have clean water, enough energy to have the lifestyle we're used to, and we need to deal with the garbage. Now, we could be idealistic, nostalgic, we heard yesterday afternoon. Nostalgic romanticism means we stop using everything that's produced and go back to the wonderful good old days. We can't do that. We've been manipulating nature since we first made fire 100,000 years ago. We've been manipulating nature since we first bred cattle to give us more milk or better meat, or we bred dogs to help us hunt, or to be our friend in the cold winter, keep us warm. So we've been manipulating nature. So this idea of going back to what the philosophers used to say, the noble savage, we can't do that. We've got a world where we've got 8 or 9 million brothers and sisters that all want to eat and breathe and drink and keep warm. Now, we can use nanotechnology to solve those problems, and I think we as geoscientists, many of us have a responsibility to use what we know to solve some of these problems. Okay, so that's what my group's doing. We're an interdisciplinary group. We have physicists and chemists and biologists and engineers, and we all work together. We learn each other's language, and that's not an easy task sometimes. We have to learn that the language of physic-ish is not so terrible, and the culture of biologyism is not unmanageable. And we manage to talk to each other and actually use our various skills, put them together, and solve some problems. So we use nanotechniques, we try to discover nature's secrets, and then we try to use that to improve something. And of course, when you improve on something, you also risk to make a new problem. And so that's why understanding is better than just mixing it around until you get the product you want. And some of the problems we're looking at, trying to do something about: ensuring cleaner water, storing waste more safely, producing oil from existing reservoirs, converting CO2 from gas to minerals. And through all that, we're learning, as a byproduct, and a happy one at that, we're learning about the mysteries of biomineralization. Now, the middle one there, producing more oil from existing reservoirs, you can't make me say that it's not important to make sustainable energy forms now. We need to start now. We need to develop and bring some of the existing technology to maturity, and we can't wait with that. I really wonder why governments aren't subsidizing alternate energy to a greater extent, but I'm not a politician. We need to be producing sustainable energy forms, but in the meantime, we just can't stop using oil tomorrow. If we stopped using oil right now, this instant, half of you would be sitting there naked because the clothes you're wearing contain oil products. The computer I'm working on, the car you drove in, or the train, lots and lots of plastics, petrochemicals. We can't stop using oil right now. So if we don't find a little bit more oil out of the existing reservoirs, that oil people tell me we've used all the easy oil. The only oil that's left is hard oil, hard to get out of the ground, hard to produce in a way that doesn't pollute, from coal, for example. So if we don't find some more, we're going to have oil prices like we saw last summer or worse. And you know what instability that causes. So society problems, that's what we're aiming at. So I would like to give you a few examples that come from my group's research to illustrate these 5 points. The first one, cleaner water and safer storage of waste. Well, this is a waste treatment plant in Denmark. Looks pretty, and they really have made efforts to keep it from polluting. They have scrubbers in the chimney that take out the fly ash, and they've tried to make reactive barriers under the fly ash disposal, because when fly ash gets wet, the heavy metals come out, enter the groundwater, and then we have a problem. So we're using information from the atomic scale to understand the processes. This here is an atomic scale image of a surface of a coccolith. Now, if you don't know what a coccolith is, I'll tell you more about it later, but it's the shell of an ancient algae, and that's what chalk is made out of. So there's lots of chalk in Denmark. We get much of our drinking water from it, and calcite's quite a good sponge for trace metals, for example. So by understanding the atomic behavior, this is the unit cell on the surface of calcite, we can understand better how the metals stick there, and then either develop better technologies or change the way we're already behaving. Okay, so one of the problems is when you make a waste dump, and here it's represented by a barrel of something toxic. When we make a waste dump, we need to line it with something that'll keep the contaminants from getting into the groundwater. In this case, the contaminants already got into the groundwater, and this is a design for a reactive barrier that treats the water as it passes through. Now, one of the active components in a reactive barrier like this is zero-valent iron. They take old railroad lines or old airplanes, grind them all up into particles that are less than a millimeter, and then the surface of that iron reacts with the groundwater and produces iron oxides, which are great traps for trace components. They have high surface area and they're reactive. But in the groundwater, where there's not very much oxygen, there's a little but not much, we don't see red rust like on your car or your bicycle. We see what's called green rust. And here it is made in the lab. It's actually more blue than green. And there's a little group within a little subgroup within my group who's been working on iron oxides for some time. And this is a picture of what it looks like in an atomic force microscope. Nice hexagonal plates, thin crystals, lots of surface area to adsorb or absorb trace components. And here you see a series of what happens when green rust oxidizes to goethite, ochre, and during that transition, trace components can be incorporated into the new mineral structure and immobilized. Now, I should tell you just a little bit about how an atomic force microscope works. It doesn't work based on light, because light has a wavelength limit of about 500 nanometers plus or minus. And many of the particles we want to look at, these are 1 micrometer wide. There's a 1 micrometer scale bar, but some of these are very much smaller than the wavelength of light, and certainly the thickness it's only a few nanometers. So an atomic force microscope works by having a sharp tip on a cantilever that's very soft, like your hair. It's really soft. It feels the forces on the surface, and then the up-down movement of the cantilever is kept by a computer, and it makes an image. So we have studied iron oxide, and we've done some some work on how it's useful in trapping contaminants, and I've chosen this as an example. Here's Lona, who's doing some experiments inside a glove box. Now, this is very reactive to oxygen, so therefore, you can't work in air. You have to work in a glove box where there is no oxygen. So she's inoculating her samples here. Here's some fresh green rust. This is made on a transmission electron microscope with our colleagues in the group of Rod Ewing in Michigan. So this fresh green rust was reacted with chromium-6. Chromium-6, it disappeared here. Chromium-6 is toxic and mobile. Chromium-3 is not toxic. In fact, it's essential for in very trace quantities, and it's not mobile. So the idea is to convert chromium-6 to chromium-3. And that's what green rust does. It oxidizes and reduces the chromium-6. And here you can see it's already entered the edge structure of this mineral. And by entering this, it's destabilized the green rust, and that's why you see these transparent rims here. It's dissolving there. And then with time, 10 minutes to 20 hours, the middle part dissolves and reprecipitates as iron oxide, goethite. And it takes up the chromium as it does that and immobilizes it. Chromium-substituted goethite is even less soluble than goethite, which some of you know is very insoluble. Don't try to get the rust off your bicycle by rinsing it with a hose. So here we see the sample after 20 hours. There's a teeny bit of green rust left there, but all of this is substituted, chromium-substituted goethite. So that's one way we can get chromium out of the leachate from a garbage dump, or to remove chromium from contaminated groundwater. Okay, the next little story I want to tell you about is a technique for seeing the pore size in porous material. This is more a physical technique than a chemical one, but if we're going to understand how water flows through aquifers and garbage dumps, or if we're going to understand how oil flows from reservoirs to the pump, we need to understand how fluids flow through pore spaces. Now, many of the techniques that we use destroy the sample. There's tomography that one can do with a transmission electron microscope or a scanning electron microscope, where you take a picture, you erode a layer, you take a picture, erode a layer, you get a lot of data. You use a computer to put it back into a three-dimensional network so you can see it, but you've destroyed the sample. So you can't put another fluid through and see how that behaves. So some members of my group have been working on this technique to develop a way to be able to analyze the same sample again and again and again, and compare what happens to the pores and to the particles as time goes and solution conditions go. Now, if I was successful in getting these movies to work, I could show you some nice little movies here, but let's make do with the plain pictures. This is a sample of chalk, and it's put into a capillary tube, and you can see here by the scale that it's about 300 micrometers wide. Now that's like a dot on a piece of paper. Not very big. And with the X-ray microtomography technique, we shine an X-ray beam, usually a synchrotron X-ray, through our sample. And you know when you go to the doctor, you get an X-ray, picture comes out on the back. It's the same with our sample. We shine it through, get a picture, and then we move the X-ray, shine it through again, get another picture, and so on, 1,000 and some times. And then we go down a layer, do it again, down a layer, do it again. We get about a terabyte of data. And then we can use that data to recreate a three-dimensional picture, and then we can take slices wherever we want and get the same on a series of samples so that we can compare one with the next. So here we have a sample of chalk that has been electronically cut out of our sample. Oh, I should say that the pixel size, pixel is a two-dimensional measure. A voxel is a volume pixel, so it's 3 dimensions. And these volume pixels in our tomography setup at the moment have about 350 nanometers of space. Now, I meant to tell you at the beginning, and I forgot. A nanometer is a billionth of a meter, 10 to the minus 9. The radius of a calcium or a sodium ion is 1 angstrom, 10 to the minus 10 meters. So a nanometer is like 5 calciums lined up shoulder to shoulder. Really small. All right, so our voxel size here is 350 micrometers. Now, a micrometer is about the size of a bacterium, to give you a frame of reference. So this is 350 bacteria lined up. Okay, so here's a sample electronically cut out. We can see the pore spaces, and we can do calculations to find out how much pore and how much solid there is. We can paint them various colors. So now here we have the solid, here we have the pore space painted blue, and the dead pores, the ones that can't transmit fluid, are painted red. And here we see the dead pores. Now, of course, this is very important to water hydrogeologists or to oil reservoir geologists, because we can measure the porosity of things, but we need to know where the fluid's passing. We need to know the pores that are really conducting fluid. And we can also paint them various colors for their pore channels. Here we have a sample of bryozoan chalk, where the water or oil would flow through along the channels that are connected. Okay, so this gives us the possibility to look and see and measure when we change the fluid, dissolve, and so on. Okay, now I'm going to have to speed up a little bit so that I can finish the stories. The next of the stories is about improving oil recovery or enhancing oil recovery from known reservoirs. And this project began with a grant from Maersk Oil and Gas, which is the biggest corporation in Denmark, probably an oil company you've never heard of if you're outside of Scandinavia. But they're very interested in chalk reservoirs. So it's fundamental research. They didn't pay for applied research, but they paid for fundamental research that has an applied end. And for me, that's the most exciting kind, because I can learn about the nature of the Earth at a fundamental scale at the same time as solving a problem. All right, so the story goes that algae, one-celled organisms, use the calcium carbonate in seawater to make a covering over themselves. And one of these little units is called a coccolith. And here's one species of algae, the coccolith from one species. Now, there are many species, and each species has its own wonderful way of designing their coccoliths, depending on their ecological niche. This is calcite, and for those who don't speak Danish, it says calcite is double refractive. There are speculations about why algae make coccoliths, but there is no real final answer yet. But it doesn't matter, because 60 million years ago, and now in present-day oceans, coccoliths produce ooze, which gets solidified into chalk. And here you see for scales and people, this is Møns Klint in Denmark. It's the Danish answer to the cliffs of Dover. And that's what our groundwater is in the North Sea basin, is kept in, and also oil. Now here we have an atomic force microscopy spectroscopy collection of data. Remember I told you about feeling the forces on the surface? We can do that and get topography, and that's what this is. Here's a 65 million year old zipper, and you can see that the elements of this coccolith, but then you can also see some things on the surface. Now it turns out these are tiny clay particles. Here's a better picture here. Some of them are only 1 unit cell thick, or 2 or 3. Now we can feel those with our tip, and we can functionalize the tip with an organic compound that is sticky or not sticky, repulsive or attractive to the things on the surface. We can functionalize it with something negative, something positive, or something oil attractive. And then we can feel the surface with this tip, and that's what's been done here. We can also feel the sponginess. You know, this has a different elasticity than this wonderful velvet-covered box here, or than the table, or than a rock. So the elasticity and the stickiness tell us a lot about the composition of the surface. Here's an example where the same technique was used to see what the properties were of a coccolith. Now this is a coccolith taken from chalk. So it's 60 million years old. And here's an SEM picture. It's, all of these are 5 micrometers wide. And here we have a topography image, feeling the topography of the surface. And we can see the remnant of a coccolith here, kind of like this one here. And up here in the corner, we can see the remnant of a rhombohedral calcite crystal that's formed by recrystallization. Now, if we feel our surface with this sticky tip, we can feel that there are some areas here. Now, pink is very sticky, and dark blue, light blue, sorry, is not sticky. So we can see that the coccolith has zones of sticky and not sticky, and this is chalk that's never been exposed to oil. So there's something there that's behaving oil wetting, hydrophobic. And in those same places, we have something that's soft, that the tip feels it as something soft. So this leads us to interpret that there's some original organic material stuck there on the surfaces of chalk that's been there since they were deposited. Okay, so we're learning about biomineralization all the way along. Biomineralization, how do bodies produce hard material? In our case, we use apatite and collagen. In the case of mussels, they use proteins and calcite. In the case of coccoliths, now this is Amelia huxleyi, it's a form that makes bloom in the North Atlantic, and you can even see these from space. So each organism uses a combination of organic materials and inorganic materials in a composite, nature's own composite materials. And our interest is finding out how they do it, because if we could understand the tricks of how these organisms work, we could maybe give that information to the medical community, and maybe they could develop treatment and prevention for things like osteoporosis and arthritis and kidney stones and all those things, where our body makes minerals we don't want. All right, well, these coccoliths, these algae-produced calcium carbonates, behave in a different way than normal calcium carbonate does. And that's quite interesting, because that has repercussions on how we're going to get that oil out of the spent reservoirs. So here we see some coccolith elements that have been exposed only to water. Now, you can see there at the edges, it's beginning to dissolve, but there's nothing in the middle. The middle is intact. There's no dissolution in the middle of the coccolith elements. Now, why? If you leave it longer, it keeps dissolving from the edges, and eventually it works in towards the middle. But there's still a large part that isn't dissolved. If we expose these fresh coccolith elements to a solution that's at saturation with calcium carbonate, so we're not dissolving from this treatment solution, and it has a strong base and a strong oxidizing agent, and we leave it for some hours, and then we rinse it off with water and leave it exposed to water for a while. Now, we don't just get dissolution along the edges, but right out there on the flat. And here you can see a very eroded calcite crystal. Now, what's that telling us? It's telling us that something that is oxidizable is coating the surface. That means that that sticky stuff we saw with the atomic force microscope must be some sort of stuff that is oxidizable. Or at least that's one of the possibilities. And that has important implications in what we do when we get the oil out. Now, I don't know if you know, when you put a hole in a reservoir, you get about 5% of the oil from lithostatic pressure. The rock's pushing down and the oil comes up. If you want more than 5%, you've got to do some tricks. And one of the tricks that was discovered some years ago is you pump water in one well and you push the oil ahead of it, and it comes out the other one. If you do that, you might get 25%, maybe 40% if you're lucky, but a good 60% on average is left behind. And it's that oil we're after. That's the hard oil. It's hard to get. All right, well, on the surface of coccoliths is these are cultured coccoliths now. People have discovered, there are the references, people have discovered that there are polysaccharides associated with coccoliths that help the calcite form those beautiful platelets. Now, we did some molecular modeling of polysaccharide. Now, that was a terribly complicated thing. You can see it here with all the functional groups and so on. So we picked out a few of those functional groups, and we did some molecular modeling on it. And now I want you to watch the calcite underneath. This is the calcite, and there's the polysaccharide. Now watch the polysaccharide dancing on the surface of the calcite. And watch the calcite molecules, the calcite ions, moving. So you see now the polysaccharide is sticking, and it's got one foot down all the time. It's kind of like us dancing. We don't dance with both feet in the air all the time. If it danced with both feet in the air, it would float off in solution again. But it's got always a foot or two on the surface. And the foot is made of hydroxyl. So that got us interested. What is it about hydroxyl that makes it so sticky? Well, here we have a sample of calcite, pure Iceland spar, cleaved, looked at it with AFM. And this behavior, this attachment of recrystallized material on the surface, this is very strange for calcite. If it's only exposed to water, it doesn't do that. If it's exposed to ethanol, OH, the OH of ethanol, ethanol is a nice one. Oh, it's gone. I had an ethanol. Ethanol is C2 with 3 H's there, 2 H's here, and an OH. Ethanol is interesting because it's the most simple OH organic material that we can use to experiment with. Water is also a very simple OH, but it doesn't have the organic component. So we exposed some calcite to ethanol, and we saw a very strange behavior. We looked at it with X-ray photoelectron spectroscopy. Now this is a technique that collects information from the very top, the top few nanometers only. And so it's very surface sensitive. So on the surface of our calcite, we can see the ethanol as these two little peaks. This is the carbonate peak, the peak for carbon stuck to oxygen. And these are the peaks for carbon stuck to OH and carbon stuck to just H's or itself, carbon-carbon. So we can see ethanol there on the surface. And we can also do some experiments with a technique called X-ray reflectivity, where we shine an X-ray off a surface and we measure the pattern that comes out. We collect the pattern and then analyze it. This is the raw pattern with bumps, and these bumps are an indication that there's different densities on the surface. So here we have a cross-section of the surface where we've got the calcite here, and we can compare that with our model. There's the calcite. And then we have a layer of ethanol attached, and we can see that. And then we have an area where there's not very much at all, and we can see that in our experimental data. And then we have the bulk ethanol out here, and there it is there. And this bulk ethanol is on the order of 20 angstroms thick. So we have a very tightly bonded ethanol layer, and then the rest. And ethanol is even more strongly bound than water. Here we see an ethanol layer, here we see a water layer, and here we see the distance, the oxygen distance from the surface. So ethanol is green, and it's more, here's the surface over here where it says 0. So ethanol is more tightly bonded than either oxygen with its, than water with its oxygen pointing toward the surface, or water with its oxygen pointing away. So in either configuration of water, it's not as strongly bound as ethanol. So what that tells us is that the polysaccharide that coccoliths produce to make that algae produce to make the beautiful coccoliths, that polysaccharide sticks to the surface through its OH groups. Now maybe we can use that to understand biomineralization and also to know what sort of a treatment material we want to put in that flooding water to get more of the oil free. And the last of the applications I'd like to tell you about is a project that I've been working with Siki Gislason, who's here on the Icelandic beach, and Eric Olkers and all their postdocs and students, where we're trying to understand, my group is trying to understand the basic fundamental processes that take place when you mix basalt with mineral water. You get silica, clay, and carbonate minerals, but there's all sorts of complications that happen. Now this is a good reaction. There's lots of basalt in the world, not only in Iceland and India and the United States and other places, but also the whole mid-Atlantic ridge. So there's lots of basalt. The free energy is favorable. It wants to go forward. The tendency is to go this way, but the rate is slow. That means there's something holding up the reaction. Now, if we heat it up, you see, there's temperature in these two equations, the thermodynamic aspects and the kinetic aspects. We could heat up the system, which they can do in Iceland because they have nice hot rocks. But in the rest of the world, you know, that's a bit of a problem. And if we use energy to make this system hot, then we produce more CO2. So that's a vicious circle. But what else can we do about this rate equation? Well, we've got a parameter there and a parameter there. If we could understand it, trees do it. Trees weather rocks. They use CO2 to produce biomass, but they also use CO2 to make organic acids and enzymes to eat up the rocks to get their nutrients. Now, if they can do it, so can we, if we can only learn the tricks. Now, I'll come back to that a little bit later. Okay, so here we are, 8 or 9 million of our brothers and sisters, and we're making a lot of garbage. What are we going to do about it? Well, there's some, we have to breathe, we have to eat and drink, and we like to stay warm. But we're not only happy with that, we also want to build things. And we can't stand it if they're not new and beautiful and big, and this is a cycle that goes on, producing more and more garbage. And we not only want to build things, but we also want to go places. And we can't change that overnight if we're going to keep the standard of living we're used to. So how can we work together? We need to work together across disciplines and across nations. We need to cooperate on CO2 taxes or trade or however we do it. We need to figure out a way to stop polluting, to use what we've got. It's not only CO2 that's a problem, it's also what are we going to do about resources. We're running low on some of the very interesting and important trace elements that we use for mobile phones and solar cells and all that sort of thing. We're producing a lot of garbage that has those materials in it. How can we get them out and recycle them more efficiently? So if we work together across disciplines and understand the world, then maybe we can solve it. Now, I personally think this is an answer. You know what this is? It's bacteria. There's one species and there's another. See the little wires this guy's got out holding them onto the surface? These guys are really smart. They know how to take things like carbon and oxygen and hydrogen and maybe some of the other elements, sulfur, nitrogen, phosphorus, some trace metals. They know how to combine those in millions of ways. These guys work cheap, and they're easy to get rid of. They only last a few hours. And they isolate, they sequester trace metals by themselves. They're also engineerable. I mean, we can manipulate these guys. We have to be careful so we don't make more problems than we solve. But these guys could help us. They could sequester the elements that we need from garbage. We could mine garbage. We could train them so that they grew coats that were only acceptable to uranium or only acceptable to indium or whatever. We could train them to make enzymes. Do you know what an enzyme is? It's a little molecule between 2 and 10 nanometers. Some are bigger, but many are small. And they're not like an acid that reacts with something and it dies. It gets used up. An enzyme is something that can react, break the chain, go on to the next one and react, and break the chain, and go on again and again and again. It's like a catalyst. So if we can train these guys to make an enzyme, like the trees do when they want to get nutrients from the minerals, then we've got an answer. Now, it's not going to be easy. We're going to have to cooperate with biotech people, with physicists and geologists and engineers and so on. We have to work together. But I really think that's where we're going. So if I was a student the age of some of you guys, I would learn geochemistry and something else. Okay, so now I've come to the end. I'd like to thank my group. I work with a wonderful group of young and old who have a great time and produce good results. We started our work about 2 years ago, and we're just now, maybe you've seen some of our presentations, posters and talks. We're just getting to the point now where we can begin to publish, because first we had to learn to speak each other's language and build a lab and get the instruments working, and now we're producing data, and it's really exciting. So we're interdisciplinary. We're gender balanced, half women, half men, and we're half Danish and half from everywhere else. And it's really, really fun. And I'd also like to thank my funding sources, without whom none of this would be possible. And you can see we're really happy. This guy got a top grade on his master's thesis 2 days ago. Okay, I think I could answer questions if there are any.